Hi, my name's Kelsey and I'm the president of the Carleton Planetary Robotics team. We're a group of students from Ottawa, Ontario, and this is our first year working to compete at the URC.
The frame group is concerned with defining the envelope of the rover and providing mounting interfaces for the electronics. For our frame, we focused on ensuring parts could easily be taken apart and replaced if needed. For the location of electronic equipment, we decided to go with what we like to call a sandbox concept, where electronic boxes can be positioned and secured in multiple different configurations onto a perforated plate.
Using ANSYS Workbench, we have ensured the various parts are capable of resisting loads that will be typically found in the field. With our detailed design completed, we are currently in the production stage of the rover, where we are manufacturing the parts of the frame for assembly. The mechanical team is also assembling small components for testing and prototyping. The chassis team is in charge of designing the motion system for the rover. The suspension is a spring dampener system that allows the rover to travel over obstacles and keep the rover steady. The rover uses a 196:1 reduction planetary gearbox to turn a wheel. The wheels use 3D printed hubs and an inner tube filled with foam beanbag pellets to form around objects and get traction.
Our team is utilizing FDM 3D printing to create prototype parts for testing, along with final parts that will be on the fielded rover for competition tasks. Some of these parts include wheel hubs and parts of the claw end effector, which will be fielded in the competition, along with prototypes for the science cache task. The arm subsystem is in charge of designing and manufacturing the robotic arm, which will be used for the science cache, astronaut assistance, and equipment servicing task. Using high torque stepper motors, planetary gearboxes, and right angle gearboxes, the arm, along with the claw, will have 6 points of motion to allow for a high precision and accuracy in order to complete the tasks.
The software team will be using Python scripts with ROS to control all of our onboard rover systems. We will also be using HTML and JavaScript for our user interfaces. The team has access to a Pioneer P3DX robot as a testing platform. Using this robot, we can test all of our software and sensors before our rover is actually built. Here we have the team using the Pioneer robot. We can see the team controlling the robot using our control user interface. We also have the ability to control the robot using a command queue. We will utilize this ability to help deal with the loss of line of sight problem. The telemetry interface provides us with all relevant data in order to monitor the state of the rover and complete mission objectives. The visual interface will provide us with a feed of any onboard camera systems. We will be using a 5-camera system in our design. We will have 2 side-facing cameras that will be able to view any obstacles around our 2 forward-facing wheels. We will have a back-facing camera to view the wagon during towing. We will have a front-facing camera whose purpose is to view anywhere our arm can maneuver, as well as a mass camera that we will use for navigation and to take the panorama during the science cache task. Using these cameras, our rover will be able to handle all possible situations throughout the competition.
High-resolution images will be taken with the mass cam to show stratigraphic profile and up-close view of the soil. Soil temperature, moisture, and electric conductivity will be measured using a 3-in-1 sensor. Electric conductivity levels of the soil are good indicators of the amount of salt and nutrients available, and it will also tell us something about the soil texture. Further analysis on the collected sample will serve to reaffirm our data collected on-site by the rover through additional moisture and EC tests. Additionally, we will test pH to further analyze the soil and assess the possibility of water and life at the site.
The science team will be responsible for the collection and analysis of the soil sample and geologic site. Currently, we have soil samples from the Utah desert area, which are being tested to gather data similar to what will be collected at the competition site, enabling a comparison as well as allowing us to calibrate our sensors.
The electrical team is mainly focused on the power and communication systems. From the power side, we have a modular design that allows us to individually control and monitor up to 32 components per board. Each board has 4 ICs, which each control 8 components. This allows us to scale the system for final rover design.
The onboard communication system will use Ethernet with a router and a switch so that all the devices may be connected. The communication system between the rover and the base station will use Wi-Fi and a point-to-point base system. We have facilities here at Carleton, such as the anechoic chamber, which will allow us to test the functionality of our communication system easily.